Hello. Can I start, Vidyadarji? Shall we start? I think.
Yeah, please.
Yeah. So again, welcome back. My name is Prithvi. I'm a PhD scholar from IIT Hyderabad. So in this week, in this session we'll be discussing about the analysis of indeterminate trusses. So in the previous class, we are discussing about the flexibility method and the use of flexibility method. And also we have analyzed some beams and also the frames using compatibility method. So in this session, we'll solve some problems on uh, analysis of indeterminate trusses. So let us start solving the problems directly. So you the concept behind solving the indeterminate trusses is, let us say we have a truss. So we have a truss something like this. So both sides pinned, and this is a simple triangular truss. We have ABC. So again, indeterminate. This is indeterminate, right? So indeterminate with uh, DS as one. So there are two possible reaction forces at each support. So we have DS as one. So let us say I have applied some load this in this fashion. So how to solve this? So for this, we actually had discussed in the last class. We what we'll do is we'll try to use the compatibility condition in this kind of problems, right? So for this, what we'll do is uh, we'll try to break down this same indeterminate structure into two determinate structures with existing loads, plus at the same time the same structure, and we'll assume some R as a reaction force for the reaction force, which has to be found out, which cannot be found using the equilibrium equations. We'll assume it as some X or R, whatever it is, and then we'll find out the internal forces in, let us say this is 1 and this is 2. We'll find out the displacement delta here, and also we'll find out, maybe it will be contracting, delta 2, delta 1 and delta 2. So we have, uh, just a second, someone just joined, let me add in. Okay. So we have, yeah, what do we have? We have sigma fx0, sigma fi0, okay, and we also have sigma m. Can sigma m be 0? Yeah, moments can also be 0. In addition, we also have delta 1 plus delta 2 0. So four reactions, we have four equations to find out the four reactions. The four reactions are, let us say, R1, R2, R3, and R4. Let us say this is R4. Yeah. So by this we can find out reactions. Once the reactions are found out, the rest of the things are straightforward. You can just simply find the internal forces in the members. That those are the axial forces in the members, and also the displacements at any point by using the virtual work method. So in this, the concept is, how do you find delta 1? Delta 1 is nothing but we'll apply a unit load at this point. Let me use another. We'll apply a unit load at this point, 1 kilonewton, and then the internal forces because of this unit load, we'll call it as U. Let me call it as U. So something like this: U1, U2, U3, and so on and so forth. and the internal forces due to the loads, external loads. So let us say this is P1, P2. Because of this, we'll get some internal forces. I'm just for time being, I'm just denoting it here. This will be F1, F2, F3. So what is delta one then? So delta one will be it is nothing but sigma FIUI LI by AE. This is delta one. What about delta two? Delta two, for delta two, you'll do the same thing. So instead of R4, what we'll do is we'll apply again here we will apply same 1 kilonewton unit load. And again we are discussing all the problems which we discuss in the present structural analysis course is mostly based on the assumption that the materials are under the elastic limit, right? So what happens if the materials are under elastic limit? So if the material is under elastic limit, the superposition principle is valid, right? So for this superposition to be valid, that means if let us say you got some delta when you are applying load 1 kilonewton. So when you apply load R kilonewton, then the displacement will be R times delta. So that's what the superposition means, right? So for this, what you'll do is simply delta 2 will be R4, okay, UI square Li by E sigma. So in this, what you'll try to do, delta 1 plus delta 2 is equal to 0, because that is our compatibility condition. So for that, let me write it clearly. Sorry. So yeah, R4 times sigma U I square Li by AE. Okay. So delta 1 plus delta 2, you just you can find out this value, and you can also find out this value. So R4 will be delta 1 by UI square Li by AE. So this is the overall concept or overall theory which we'll be using it which we'll be using in the today's problems. So we'll try to solve a few questions in today's problem, and then maybe with that we'll try to understand actually what and how to analyze the indeterminate trusses. So maybe we can take one problem with external indeterminacy. So in this, it is externally indeterminate, right? Like external, like I said, the supports itself, the support itself, we can't solve the support reaction itself using the equilibrium equations, right? So maybe one question we can take with external indeterminacy, and one question we'll take with internal indeterminacy. Okay, degree of internal indeterminacy as something more than 0, and one question will solve with degree of indeterminacy with internal indeterminacy as greater than 1. Okay. So let me just take first question. So first question is we have a truss. Again, I'm taking a very simple question. We have a truss. Yeah. Now truss is kind of a pins up, both sides pinned. Okay. So we have a truss, and the distance is yeah, we fine. So the distances are so and so. I'll just mark the distances. This is 8. This is 8. I can take it as 8 meters. 8 meters. This is too large, but I think the cross sections are too. Maybe the cross sections are uh, cross sections. The area of cross section, I think it's very too large. Maybe that's the reason why they have taken 8 meter span. So and also the height it is given as. Let me check it. Yeah, this is 8 meters. Even the height is also 8 meters. Okay. So the truss uh, is loaded. I mean, it's loaded with different types of load. So one, this is we have a load of, we have a vertical load here, and also we have a horizontal load here acting. So this is 30 kilonewtons, and this is 30, is it 34.6, okay, 34.6 kilonewtons, okay. And yeah, that's yeah, that is all about the question. Okay, there is one, okay, there is one more load acting here. It is 20 kilonewton. Okay, so the first, let me note down. This is A, B, C, and D. So the first step is to find out the degree of indeterminacy. So ds can be found as, we have four reactions, something like that. So we have four reactions generated, but we have only three equations of equilibrium. So the degree of static indeterminacy is 1. So the next step is to actually break down this statically indeterminate structure to two different statically determinate structures and apply the compatibility equations. So what I'll try to do is, here I'm just scaling it down and I'm drawing it smaller. So the same can be written as a simply supported. You have 30 kilonewton. We have 34.6 kilonewton, and there is also one more load which is 20 kilonewton acting here. And this is another. This is also another. Yeah, this is another one, the same one, but we what is, so I'm choosing the horizontal reaction at C as my redundant force. Okay, so I'll write it as, let me name it now itself. So this is vertical at A, horizontal at A, vertical at C, horizontal at C. So what I'll try to do is I'll try to push this HC here. So this is my redundant force which I'm applying externally. So the concept here is we want delta 1 to be, so let me take this as delta 1, and let me take this as delta 2. So delta 1 plus delta 2 should be 0. Okay, so now how to find delta 1? Now each problem itself will be another that itself will be we need to solve for each one. So let me solve for one. So I'm just calling it as truss 1. So by now I think we are very comfortable with solving the internal forces, or the forces in the truss, right? So what I'll try to do is I'll try to write down the forces here. 30 kilonewtons. We have this, and this is so and so. This is 20, and this is 34.6. So the reaction forces will be 34.6, right? So 34.6 uh, will it be balanced? It will not be balanced because you have 30 coming there, right? So 30 times 8, 30 times. Let me just calculate only for this. I think rest of the things I can directly write it down, but only for one. Maybe for the calculation purpose, I'll just solve this. So that, yeah. So the reaction forces will be, so this is one reaction force, and this is the other one. So 30 times 8, 30 times 8 plus 34.6 times 8 divided by 16, that is 32.3. Is it? I think I made a mistake in taking the length of the beam. Yeah. Anyways, we can go ahead with this. So this is 32.3, and this should be how much? 32.3 minus 34.6. So this is 2.3. Okay, and we only have the reaction force coming from this side. So this is 30 plus 20. That is 30 plus 20 is 50. So let me write 50 here. This is 50. Okay. So this is one part, and what is the other part? So the other part we need to apply the virtual force, the virtual load, right? So the virtual unit load. So usually we call it as unit load directly. So let me apply a unit load of 1 kilonewton. So this is unit load of 1 kilonewton. When I am applying 1 kilonewton load over here, right? So what happens? So yeah, with this you can simply try to formulate your internal forces. I'll just write the internal forces only for this truss one. For the rest of the truss, maybe you can it's easy to find out the internal forces. So I'll just leave it for you. So let me write the internal forces here. So what happens? This is 2.3 kilonewtons. This is 50. So this is 45 degrees. So let me call this as AB, right? AD, and this is B, and this is C. So FAD by root 2 should be equal to minus 2.3. That implies FAD is minus 2.3 root 2. Okay, so this should be around minus 3.33. That means it is compression, right? Let me write minus directly here. Minus 3.225, sorry. And minus 3.25, it's in compression side, so you should have a tension here. So the tension comes here. So 3.25 uh, 3.25 divided by root 2 again. So that is root 2. That is 2.3. So 2.3 plus 50, that is 52.3. All right. So if it is 52.3, you have extra 20 kilonewtons which is pulling in this direction, right? So the rest, so the what is the net force there? 52.3 minus 20. So that will be 32.3. So this is going to be 32.3. So what about the vertical force? So like I said, this is a junction, right? So you have only vertical force acting of 34.6. So there should be tension 34.6. So what is going to happen in DC? So in DC, I'll take 32.3. So FDC, let me write it. FDC square root of 2 should be equal to 32.3, but this should be in compression, right? So this should be in compression. So 32.3, 32.3 square root of 2. So that is 45.69. So 45.69 in compression. Okay. So this I have solved for maybe you. This thing it's almost it's kind of direct. So this is 1 kilonewton. If this, so there is no force in this, and if this is 1, this should be 1. If there is no force in this, right? So this happens to be if this is 1, and yeah, this is also 1. So do we have any vertical forces coming anywhere in this beam in the virtual? I mean, with the on the truss with virtual load or with the unit load, there is no vertical forces coming, right? So there is no forces in these members. So we need to yeah. So what happens for delta 1? So delta 1 can be written as FIUILI by AE is constant. Okay, so I did not mention about AE, but AE is constant in this question. So this is about delta one. So as we see here, this term is zero, this term is zero, this term is zero, right? So we have only A, B, and B, A, B, and C. Only these terms will be making some significance to towards our the deformation formula, right? So for that, what we'll try to do is it is 52.3. F1 is 52.3. This is intention. So that is 52.3, and U is going to be 1. Li is 8 meters divided by AE plus even in BC we have 32.3 as our tensile load, and uh, okay, this is compression. I'm sorry. So this is minus. So this is minus 1. Uh, 32.3 tension minus 1 compression, 8 meters length by AE. So this is found to be 52.38 plus 32.3 times 8, 676. 676.8 by AE. So this is minus. Okay, this is minus. That means what does minus sign mean? So minus sign means the the displacement, actually, where is it? So the displacement is opposite to the applied force, so actually the displacement is in this direction. So the delta one which we assume is the right, so it's actually moving towards the right side. The joint C is actually moving towards the right. Okay. Now we have analyzed for truss 1. Now what about truss 2? Truss 2. Okay, truss 2. So let me just draw the truss 2. Oh, sorry. Yeah. So for truss 2, we actually apply the redundant force there, right? We apply the redundant force of how did you apply here in this, in which direction? To the left. Okay, let us apply to the left itself. So I'm applying redundant force. We mentioned it as HC. Yeah, HC. Let me write it as HC. HC. Okay. And we need to find displacement. So we will get some displacement. This is delta 2. So how do you find displacement? Again, it is quite similar. For HC, we'll find what are the internal forces, and also we'll apply a unit load 1 kilonewton in the same direction to find out our internal forces. So we already know that the unit forces are 1 and 1 here, right? So the forces here are 1, and then for the unit load, right? So if it is for HC, it will be HC and HC with the same sign, because we are applying the virtual load or the unit load in the same direction as HC, which we have applied earlier. So what happens in this case? So we need to delta 2 is nothing but sigma ui square li by AE, this whole thing multiplied by HC. Okay. So ui square, again, as we know, it is minus 1 square into 8 divided by AE plus minus 1 square into 8 divided by AE, whole thing multiplied by HC, is going to be 16 by AE multiplied by HC. Now what is the compatibility condition? So the compatibility condition is delta 1. So we need to, again, this should be an algebraic sum, right? So in this, the delta 1, even though we have assumed it in this direction, I think yeah, this is minus, so minus is actually in this direction. Yeah. What about in this? So if this is positive, right, that means it is going to be in this direction. So 676.8 by AE should be equal to 16 by AE, or otherwise we can simply say something like this: minus 67. Sorry, let me write it. Delta 1 plus delta 2 should be equal to 0, minus 676 by AE plus HC times 16 by AE should be 0. HC is going to be 676 divided by 16. 676 divided by 16, that is 42.25. That is going to be 42.25 kilonewton. So by this we found out what is HC, which we are not able to find using only the equations of equilibrium. So we had to adopt the compatibility equation, equation in this case. So once we have found HC, the rest of the things are direct. So we know what is HC. So this is 30 kilonewtons. This is 34.6 kilonewtons. Sorry. This is 20 kilonewtons. This is a pin support. This is a pin support. So HC is 42.5, right? So this is in the direction of the assumed. So how do we assume? We assumed it towards the left. So that has to be included here. Okay, once this is 42.25, then the vertical forces will not change. Okay, the vertical force will not change. This is 2.3. Is it right? 2. How much is it? 2.3 and 32.3. 2.3 and 32.3. So what is going to change? So 30 plus 20 is 50. 50 minus 42.25 is 7.75. So this 7.75 is going to act like this. 7.75 kilonewtons. Yeah, once you know all these things, I think it is now almost the problem is solved. You need to just find out the internal forces. What are the internal forces? So internal forces can be found, and and also yeah, you can also found various parameters like the displacement at this point, the displacement at this point, horizontal and vertical displacements, etc. So in this question, we actually solved. If we have external static indeterminacy, how do we find the redundant forces, or how do we find the support reactions, or how do we find the internal forces? So any questions in this any doubts or any questions?
No. No.
Yeah. Okay. Thank you. So let us solve one question. Next question on the similar this uh, or else let us take a question on internal indeterminacy this time. So we have already solved for external indeterminacy. Let me take one question with internal indeterminacy, and let us see how it can be solved. So we have a question. Again, it is a simply supported truss. So we have a simply supported truss, something like this. So yeah, this is fine, but this is unstable, right? This is not stable. So yeah, now this makes it stable, but this makes it a little complicated. Okay, so what I have is I have a hinge. I have a hinge here, and I have a roller support here. Okay, so okay, I have a load. Okay, I will just I have a load of 10 kilonewtons acting here, 20 kilonewton acting here, and 15 kilonewton acting at this node. So this is going to be A, B, C, D, E, and the distances are this is 2 meters, even this is 2 meters. The height, which is important, so the height is this is also 2 meters. Okay, so yeah, again, first question is whether it is statically indeterminate. First let us find external indeterminacy that we can see by inspection. We can say that it is statically determinate externally, right? So, what about internal indeterminacy? So, internal indeterminacy, yes, there is there is uh, 1 degree, right? It is internal indeterminate by degree 1. So that you already have this formula m plus r minus 2j. Uh, anyway, so with that, what we'll find? We'll say m plus r minus 2j. Number of members we have 1, 2, 3, 4, 5, 6, 7, 8. 8 reaction forces 3 minus 2, 1, 2, 3, 4, 5. 11 minus 10, that is 1. Okay. Mind you, this is not the joint. Okay. So yeah, internal indeterminacy is 1. As we can see, it is crisscrossed, right? The diagonals are crisscrossed. So again, it actually gives up gives us one extra indeterminate, or we need one more equation in addition to the equilibrium equations to solve for that member forces. So yeah, again, I just want to repeat this again. So as we already mentioned before, this indeterminacy, the degree of indeterminacy which we are trying to find, right? So this is not only this does not hold for only finding out the support reactions. It also holds good for once you find the support reactions, it should also be easy for you, or it should be directly, or it should be direct application of the force equilibrium equations to find the internal forces also. So last time when we discussed about the frames, right, different storied frames. So in that we are also discussing about the internal indeterminacy also, right? So it also becomes important for us to know whether the structure is internally indeterminate or internally determinate to to find out various member forces. So yeah, in this again, this is one of the example of internal indeterminacy. So what I'll try to do is yeah, for this kind of questions again, what again we'll follow the same similar kind of approach which we have used for the previous questions. Okay, so in this we'll try to make a small cut over here, like as I show. We'll try to cut the member. So in this, I assume that member BE, okay, as a redundant force. So redundant means that we are not able to find that force using the equations of equilibrium. So what I'll try to do is I'll just cut that member, and then I'll try to pull it. I'll try to cut that member, and first initially I'll try to make it as a determinate truss internally as well as externally, which is already it is. So I'll try to make it in determinate, and then I'll try to find the I'll try to find the displacement of the joint BE. Okay, I'll try to find the displacement of the joint BE. Later, I'll try to apply an external force BE. Okay, without any existing forces, and also I'll find out the displacement in the joint BE. Okay, how much relatively the joint BE has moved. So I'll just show what I'll try to do. So let me again scale down my question. So what I'll try to do is initially I'll just cut my section. I'll just cut it like this. Yeah, I'll try to cut this. Yeah, please assume this as diagonal. So I'll try to cut this, and I'll try to find. I'll try to find. So this is cut. Okay, so I think there is no. See, once you're cut, that means there's no force inside those members, right? That means it is not at all a diagonal. It is just simply hanging there. So what I'll try to do is with the external loads. So these are my external loads. So I need to draw this a bigger arrow. Yeah. So this is 10. This is 20, and this is 15. 15 kilonewtons, 20 kilonewtons, 10 kilonewtons. So what I'll try to do is I'll find out. Yeah, we were following delta 1, right? So I'll take this as delta 1. Okay. Again, to find delta 1 itself is again a problem, right? So to find delta 1, what we'll do, we'll try to apply a force, a unit force in that direction, and then you'll find out the internal forces in the members, and then you'll use the delta sigma FUL by AE. So this is one part, and what is the next part? Next part is I'll take the I'll take the truss. I'll apply force. Now this is my redundant force, so I'll call this as FBD. FBD is my redundant force, and in this again I'll find out what is my delta, which is displacement, and that is nothing but delta 2. So my uh, delta 1 plus delta 2 should be 0. Okay, so yeah, that is all. This delta plus that delta 1 should be 0. So you should not have any relative displacement inside, right? There can be shortening or shortening, or maybe the member can stretch by itself due to internal forces, but there should not be any relative displacement between the initial delta 1 and delta 2. So delta 1 plus delta 2 should be 0, and by using that equation, you can find out what is FBD, which is redundant force. So again, I'll call this as 1. This is 2. So let me start with 1. Truss 1. I'll start with truss 1. So truss 1 is nothing but, let me draw it again. I'll draw it neatly so that we can. Yeah. So this is my truss. What did I assume? Yeah, this is my member. So this is 10, 20, 15. Okay. Right. All right. So and okay, I have I'm just scaling down, and then this is my for my. So this is my load, internal force or internal load as 1. Okay. Again, you may ask, like, why do we need to take 1 kilonewton both sides? So again, this is very simple. So we are actually finding out the relative displacements between BE. So that is the reason why we are actually trying to pull B and E together. Okay, so we want to find out this the forces in FB, right? So like, see, at the end, our at the end, the objective is to find FBD, right? FBD will not only see that is not going to FBD is not going to act only like this, right? There is always an opposing forces, right? FBD in this direction also. So again, yeah, that is how we are trying to formulate this. Anyway, so this is one. Uh, we have pin support here. We have a roller support here. Now again, this is again we need to find out the reaction forces. I'm just trying to mention a few reaction. Maybe V E A. What is this? This is A B C D E. So V E is going to be. I'm just finding out V E. So I'll take moment at C. So for C, it should be 10 times 4 plus 20 times 2 divided by 6. That is going to 46. 40, 40, 80. 80 by 60 is it 60? It's no, sorry, it's 4. Sorry, it's 4. So 80 by 4 is 20 kilonewtons. Then VC will be vertical at C is 10, 20, 30. 45 minus 20 is 25 kilonewtons. There is no any external horizontal forces, so there is no horizontal reaction at E. So V is going to be 20, VC is going to be 25. Yeah, once we know this, I think this can be easily found out. uh, this is upper 10, so this is going to be 10, so the 10 should be resisted by this is going to be compression, no sorry, this is 20, so this is going to be 10. Okay, in tension. What about this? This is going to be 0 because there is no force in this. Fine, all right, then what about this member? So 25 root 2, let me just solve for this. F, let me solve for this. F BC cos theta. So cos theta is for, okay, I didn't. I hope you have noted it down already. 2 meters. This is 2 meters. This angle is 45. That means this length is also 2 meters. So FBC or SFCB, whatever it is, cos theta, that is square root of 2. That is equal to, how much is that? 25 minus 10 is 15. So that is going to be 50, sorry, 25 minus 15 is 10. So FBC is 10 root 2. So 10 root 2, it's in tension, so I'll just mention it as 10 root 2. Next, FCD. FCD is nothing but, FCD is nothing but, what can I take? F 10 root 2 by cos theta, that is again root 2, that is going to be, this is going to be in compression, so this has to compress it. So this is minus, so this has to compress in this direction, and this is 10 kilonewtons. What about FBD? FBD or FBC? We have FBC here. Where is it? FBC is done. Okay, sorry. FBD. So FBD. FBD is nothing but FBC cos 45 square root of 2. That is going to be 10 root 2 by 10 root 2. That is going to be 10, and it is in compression. So FBD is going to be compressed. So this is going to be compressed 10. Now FAB. FAB is nothing but again 10 root 2, which is nothing but FBC times cos root. This is 10. So this is going to be 10, and it is tension. This is tensile. So this is tensile. And yeah, FAD is again, so FAD, you can see this is again a resultant of it, right? So you are pulling AE in 10 upwards, AB 10 upwards, so you'll have a resultant along AD of 10 root 2, so that has to be resisted by AD, that should be, then it should generate a compression force 10 root 2. Okay, so this is going to be 10 root 2, and for time being I'll just mention the signs also. Minus 10, this is 10, this is 10, this is minus 10, this is minus 10, and yeah, the rest of it is 0. I'll solve this in the next sheet, I think. Let me solve this in the next sheet. So I have this truss member. We have this here, this one, and the internal forces, right? So what is the internal force? So this is my internal force. So I'm pulling it something like this. 1. So this is my pin connection. This is my roller support. So if it is 1, so here I'm just writing it down. I think I don't think I need to mention it. So I'll just, this is in tension, this is 1, and this is going to be minus 1 by root 2, and this is going to be, so 1, right? So 1 times square root of 2, that should be, that will give its component in tensile force, so that has to be resisted by this force by in compression. So that is 1 by root 2. So this is going to be minus 1 by root 2, and so if this is minus 1 by root 2, this is minus 1 by, so yeah, this is again minus 1 by root 2. Okay, So what happens to the rest of the members? So rest of the member, there is no force here. There is no force at this roller support. There is no force at this roller support and this pin support. So if there is no force, this should go zero. So there is no forces in that. So this is my UI. Okay. Uh, let me take the redundant force also now. Okay. What I'll do is I'll take the redundant force. So for the redundant force, it is again it is similar to the unit load, right? Sorry. So for the redundant force, where is my redundant force coming from? So my redundant force, as you can see, it is something like this. So what am I calling it as? FBE, right? So FBE. So if for this redundant force, as you can see, uh, my what will be my UI? This is delta two, or nothing but the displacement, the relative displacements. So what is this going to be? Okay. So for the first one, let me, yeah, now we have analyzed this. So this is again going to be, this is going to be minus, I'm writing as f only, f instead of fbe. This is minus f by root 2. This is minus f by root 2. This is minus f by root 2. And this is also minus f by root 2. Okay. And this is going to be tensile f. Now so delta, first let us find what is delta 1. Okay. So delta 1 is nothing but sigma fi ui li by ae. So only consider this part and consider this part. Okay. So I'll just write down, maybe we can make a table or column, and then it will be easy for us to write down those. So we have member, length of the member, fi, internal forces due to the externally applied loads, and we have ui is the internal forces due to applied unit virtual load, and we have fi ui li, and we also we I think we need to take, what we need to take, we need to take ui square li. Okay. So now we have members, member ab, bc, cd, bd, de, ae, be, and ad. So these are the members which we have. The lengths are two. I'm writing all the lengths in terms of meters. So okay, let me mention here. M in meters, kilonewtons, U in kilonewtons. This thing, okay. So BC is 2 root 2, 2 meters, 2 meters, 2 meters. This is 2 meters. BE is again a diagonal element, so it is 2 root 2. AD is also a diagonal element, 2 root 2. So FI, so we already have 10, 10, minus 10, 10 root 2, 10, minus 10 root 2, and 10, right? So I'm just noting it down here. So Fi is going to be 10 for AB, BC it's 10 root 2, CD is minus 10 compression, BD is minus 10 compression, 0, 10, BE is going to be 0, PE is going to be 0 because there is no force in it, right? We have assumed that we have removed the support, we have removed the member BE. So this is minus 10 root 2. Now what is happening for UI? UI is nothing but the internal forces. So minus 1 by root 2, 1 by root 2, 1 by root 2, 1 by root 2, right? And 1. So we have only 1, 2, 3, 4, 5, 5 forces. So what I'll try to write is minus 1 by root 2 B6 0, CD is also 0, minus 1 by root 2, minus 1 by root 2, AE is also minus 1 by root 2, BE, what is B? B is actually 1, AD it's also 1, positive. So FI, UI, LI, so 2 by root 2 into 10. So root 2 into 10 root 2, 10 times 1.414, it's 14.14. 14.14. This is 10 times 20, 20 times 240, but we have UI as 0. So minus 20, again this is 0. So 10 root 2, this is again minus 14. Is this going to be minus times plus? Yeah, this is, this is 14.14 positive. This is minus 1.1, minus DE, right? DE is 0. Sorry, DE is 0. A is going to be minus 14.14. 2 root 2 is 0. Minus 40. So when you sum, let me come to that summation part later. So this is ui square. So this is going to be ui square into L. Okay. So 1 by 2 is 1 by 2 times 1 is 1. 0 0 1 1 1, and this is going to be 1 square times 2 root 2 is 2 root 2. 2 root 2, 1 square times 2 root 2 is 2 root 2. So this is going to be 1 2 3 4 4 plus 4 root 2, and this is going to be minus 54.14. Okay. Now what is our delta 1? Delta 1 is nothing but sigma fi li by ae, right? So with this, what we try to find out what is delta 1, that is minus 54.14 by ae. What about delta 2? Delta 2 is going to be uh, FBE times sigma ui square li by ae, and that is going to be FBE times 4 plus 4 root 2 by ae. Now now what is the compatibility condition? Compatibility condition says that delta 1 plus delta 2 is 0. So with this we can say minus 54.14 plus 4 4 plus 4 root 2, 4 plus 4 root 2. Again we have taken a is constant. If the a is changing, then again you need to include that in the summation part. So in that case you will have ai also. Okay. But in present in this question we have taken a is constant. Okay. So this is going to be FBE, that is equal to 0. FBE is going to be 54.14 divided by 4 plus 4 root 2. So FBE can be written as 5.606 kilometers. So the assumed direction is correct. We are actually assuming it. We are assuming that there is a tensile force in FBE, and we obtain the tensile forces in FBE. And also, how do we find the internal forces? So internal forces, it's very direct, right? Because you again we are using the degree of superposition here, right? So what we'll do is initially the forces are the PIs. So you can see the forces are 10 root 2, 10, 10, 10 and 10 root 2 and all. This part, right? So you just add x. Why you need to add xi? So I'm not telling you directly to add it, but you have this. Okay, let me just tell you. So this is one, right? So we already have this one, right? This is 5.61. So because of this 5.61 we already got. So this is x by root 2 or f by root 2, something like that. So you can directly add these things to the existing values and you can find out. Let me just write down the final analysis or final forces in the members. So yeah, so we have 10 kilonewton acting here, 20 kilonewton acting here, 15 kilonewton acting here, 10, 20, 15. So what I can say is, yeah, A, B, C, D, E. So AB is going to be 6.04. BC is going to be 10 root 2. CD is going to be minus 10. DE is going to be minus 3.96. AE is going to be 6.04. And BE, what is BE? BE is going to be tensile. So this is what we have found, right? 06, 5.606. And what about AD? AD is going to be compression. It's going to be in compression, and that is 8.536. So this is how we will find out the internal forces for statically indeterminate truss with the indeterminacy or with the degree of statical indeterminacy at with internal indeterminacy and the degree as one. So anything to discuss in this? Any doubts in this, or you want some clarification? Okay, I'll move on to the next question. So the next question is, let me take one question where we have different types of boundary condition or different types of, let us say, okay, let me just give you a hint of how to solve if there is some temperature temperature effects or something like that. Okay, so what happens in a truss? So in a truss it is actually subjected to sometimes you may have sorry so you may have variations in the temperature. So because of that temperature there can be some thermal strains, right? Thermal strains, what I mean is it can if the temperature is increased, the members can expand. If the temperature decreases, the members can contract. So how does the temperature effects is considered in the analysis? Okay, so let me take one simple question. We'll just take one simple question on how to incorporate the temperature effects. So let me just take this question. Just a minute. Yeah. So we have a question. Let me just say how to actually solve for this kind of a question. So we'll have a beam. Sorry, we have a truss. Okay. This is a truss. Right now, let us just analyze for indeterminate, and then we can just try to include this for indeterminate truss also. So this is a determinate truss. What happens is that, let us say there is a we have the length as 2 meters, and this is also 2 meters. We can also have external forces acting on it, but for this question, I just take that there's no external forces. Only thing which was said is the members, uh, the, and maybe because of welding or because of heating, maybe because of locally heating it or something. The member AC, if it was asked that the member AC was subjected to the change in temperature or the increase in temperature to up to maybe let us say 40 degrees. Okay, the delta T of AC is given as 40 degrees. We have thermal coefficient for the steel. It's 11 into 10 power minus 1 per degree Celsius. Uh, and we know that, right? So we have AC. The length of AC is given 2 root 2. So what is the displacement, or let us say what is the displacement at C because of that also. So horizontal displacement at C is how much, or delta HC is how much. So how do we find this? So this is again a simple question. This is similar to what we are solving earlier. So in this case, uh, we don't have FIs, right? So FI, whatever we are doing, what is FI? So for FI, we are taking a truss member and we are loading it with the external we are having the external loads coming onto the member, and then we are finding the internal strains. So if again, if you remember the principle of virtual work, sorry, the principle of virtual, what does it says? 1 times delta is nothing but sigma Fi Li by E times Ui. Okay, so these are the strains actually. So these are the strains. Uh, is it strain FL by E is delta? Sorry, these are the deformations, and this is due to internal forces along that member due to externally applied virtual unit load. Okay, so this is already given. That's what it says. So it says that the member the diagonal member AC is heated to a temperature 40 degrees. The delta T is about 40 degrees. So this is already given. So you need to just find what is UI. So what happens is this, and what happens is that, so we have U. Let me take the same truss. So I need to find horizontal reaction. So this is 1 kilonewton. So if this is 1, this is going to be 1. This is 1, so this is 1, and this is 1. Okay. So this is an advantage for taking uh, the dimension same. So we have 1, 1, 1, 1 everywhere. So if this is 1, this is going to be 1. We only require AC, right? Rest of the things we have, not the force is 0. Oh, sorry. The forces are not 0, but I only need this because F L A F I L I by AE in these members are zeros. Okay. So what I'm going to do? So for this, uh, yeah, what is my? So I have this way. So it should be in this direction. So this is square root of 2. So this is square root of 2. So if this is square root of 2, uh, what is my delta H? Delta H is going to be FILI by AE is already given, that is alpha delta T. Okay, this is my displacement. PL by AE, that is nothing but the delta, right? So instead of PL by AE, here we have thermal expansion. So due to thermal expansion, we have the displacement as alpha delta T into L. Sorry, I forgot Li. So alpha delta T times Li, or L, times Ui is going to be square root of 2. Okay. So alpha is 11 10 to power minus 6, delta T is 40, Li is 2 root 2 times root 2. So this is going to be 4, uh, 160, 11. How much is that? 160 times 11 to 10 to the power minus 6. Yeah, this is going to be 1.76 into 10 to the power minus 3. Is it mm? No, meters. So this is going to be meters. This is meters. So delta H is going to be 1.76 mm. So this is pretty straightforward. You can see if the given truss, in the given truss, if AC is actually heated and the delta D, the difference in the temperature is about 40 degrees for the AC, where the rest of the members are not touched or not even not at all. There's no influence of the temperature for the rest of the members. So it will move that the point G or the point C, the joint C will move horizontally by 1.76 mm. Okay. So this is how we usually include the temperature effects in our calculations. Uh, that is how we analyze the trusses for. So, any questions in this?
How to convert it into the force developed?
Forces?
Force developed in the member.
Yeah, this is
This will
again.
be another.
Yeah,
This will be additional force. Additional force will develop in the member AC. No?
true. Yeah. So see, once you find out what your PL by AE, see the alpha delta T Li is nothing but PL by AE, right? So P the force will be your alpha delta AE. So if you know this force, right? So this force is PL by AE. Sorry, this displacement is PL by AE. So that PL by AE is going to be alpha delta T times L. So L cancels. So P is going to be alpha delta T times AE. So once you know P, the rest of the forces it is direct because it is an indeterminate structure.
Okay.
Yeah. So with this actually we can find out even the vertical displacements and also the horizontal or and also the roller how much it has moved in horizontal direction because of the change in temperatures. So there is one more type of problems in this is this usually happens at the construction site. So usually we'll so you as you know this is 2 root 2 that means 1.4 2.28 so 2.828 so there should be 2.828 what if it is too short so you need to pull it and you need to like for example what happens if it is too short that means let us say the member AB let me take a new so member this is AB so member AC is too short and it is short by too short and it is short by say 10 mm. Okay, so it has to be this the initial length should be 2.841428 mm, but now it is only this much, not to the scale 10 mm. So 10 is like sorry, this is 2 meters, right? Sorry, I just messed it up. Just a second. This is 2828 mm. So this now it is like 2818 mm. This is too short. So what we'll do, we'll now right now we don't simply fabricate somewhere here because the gusset plate or whatever the plates or the joining plates which are available, they are located at that distance only, right? Two and two at that grid locations. So we need to pull it. So usually we'll be pulling it and then we'll be fixing this. So when we pull it, usually we are actually inducing a tensile force in it. So but when you pull it and when you anchor it there, you get a compression forces in it, right? So it has a react compression force reactive. The reaction developed is a compressive force. So with this, what happens? So PL by AE that is going to be 10 mm in this. So you can directly take, instead of fi li by ae, here we have taken alpha delta t into li, right? Instead of this, you can directly take 10 mm, and then you can take ui to find out what, how is it going to affect the joint displacements. So this is also one type, another kind of a question where usually we see for the trusses. So one is the members getting heated up or it's getting cooled down. I don't know. In India, I don't think will. Uh, uh, I don't think there's too much temperature differences. Anyways, like I think 40 degrees is also too much actually. Even in summers, I don't think there is a 40 degrees temperature daytime and in the night time. I'm not sure. But anyways, if you are welding or maybe you're trying to flame cut, sometimes you will be doing some flame cutting and all that. It uses some kind of thermal loads or thermal stresses inside the members. So because of that, maybe the member can try to expand due to this thermal loads. That is one type of question. And second one is, what if the member is too short or too long? So sometimes it can also be long. So you will compress it and then you need to you will tighten it at the gusset plates, and then it also includes some kind of displacements or extra forces which are not actually intended to be, but those are forced into the members. So this is what I actually wanted to cover in this tutorial, because in the last class I think I have taken a lot of questions on beams and frames. So for the trusses, I think it is similar to all these things. For example, let me take one more question. I'll just uh, I'll just uh, I'll just say how it can be solved. The rest of the things I think it is easy. It is again direct, so I don't want to just uh, repeat the procedures. I'll just take one more question. I think this is, in this question there are it has the degree of redundancy is 2. Where is that question? Let me take that question once. The degree of redundancy in this is 2. Yeah, this is the one. So I'll take a fresh page. So we have a truss. We have a truss member. So we have a, yeah. I don't know why it is crisscrossed. Like maybe I'm not sure, but this looks very asymmetric. So anyway, so usually we can see these kind of things on footover bridges. So most of the footover bridge kind of structures you can see these kind of things, but anyways, it will not have any intermediate supports because that is not possible. So let me maybe in this question, what is degree of static indeterminacy, degree of external indeterminacy and internal indeterminacy? So we have ds going to be m plus r minus 2j. I'm not going to solve this by now. We can say by intuition we can solve for this. So we have one extra force here and one extra member here. So this is 2. So we have two different forces here, right? So how do we solve? So initially, what we'll do, we'll just remove this. Uh, Let me just so we'll remove this support. Yeah, I'll just remove my redundant forces here. So what I'll do, I'll apply unit load here. How much I need to apply? I need to apply a force of 1 kilonewton, right? So this is my okay. Initially, I'll be having, you have some loads, external loads, so you'll be applying 1 kilonewton here. At the same time, you also apply force. You also apply a vertical reaction force here. So this is going to be, so you are going to apply a vertical reaction force here. So with this, what you are trying to find, you're going to find uh, delta 1 and delta 2, right? So with this, you can find what is delta 1 because of the force, because of this force. So you have you'll have delta 1. So because of the uh, what do you call it, because of the redundant force F, this is F, let us say this is a reaction R. So in this you'll have two different forces. So because of F, what is your this is delta 2. So because of F, you have delta 1 and delta 2. Okay, and also because of R, you will have, let me call it as delta 1 dash and delta 2 dash, 1 dash and delta 2 dash. Okay, so how do we solve for this? Again, this is again similar, delta 2 dash plus delta 1 dash, that should be equal to 0. Delta 1 dash plus delta 1, that is going to be 0. So once you solve for this, you can find out what is, you have, again in this you'll have two different, delta 1 plus delta 1 dash is 0, delta 2 plus delta 2 dash is 0. So you have two degrees of redundancy, right? Two as a redundancy, so F and R. So with these two equations, you can find out what is F and what is R. So this is like, you can have n number of redundant forces, and you can find out, you can always formulate, uh, if you have n redundant forces, you can formulate n compatibility conditions, and then you can find out the compatible, you can find out the redundant forces from that. So this is what I wanted to discuss for this session. So you have any doubts or anything which you want to clarify?
I think can we discuss the procedure in brief of this?
For this question?
Yeah.
Yeah,
First
sure.
we'll,
Okay. Yeah. Let me just write down some steps. I'll just write down
yeah,
some steps. Yeah, that will be helpful. Sure, definitely. Let me just yeah. So what? Let me write down the question itself. So I did not write the question completely because I did not. So what happens in this is, like, let us say we have, so this is the question, and we have a horizontal force of 70 kilonewton. Okay. So this is A, B, C, D, E, F, G, and H. So at B you have a vertical force. Okay, this is also given 80 kilonewton. 80 kilonewton. That's it. Yeah, this is 10 meters, and this is 4 by, this is 4 number of spans, each one spanning 10 meters. Okay, in this question they also mentioned the E is 200 GPa. So usually trusses, usually we have it the metal members, right? So because again we assume it as a hinge support, hinged connections. So it is very difficult to get a hinge connection for a concrete members, right? Anyways, concrete we can't utilize it in tension, so that is one of the reason maybe we can't use concrete members for the truss members, right? Uh, Whereas the metals usually it has a symmetric behavior. I mean, not symmetric. It's what do you call it? It has the same behavior in tension and compression. So in trusses, you can't simply have only compression coming, except not except. I think only for the arches we can get the compression. So that is the reason why in the arch members or in various arch, like we have a lot of dams in which it's an arch dam and earthen dams. Those are kind of an arched members, right? So in that we can actually obtain the compression forces in the members. So there we can utilize concrete because uh, concrete performs highly or very concrete performs well in compression, right? When compared to in tension. Anyways, okay, that is not the scope, but area is again 4,000 mm square. E is 200 GPa, area is 4,000 mm square. And did I miss anything? A, B, C, D, E, and F, G, H, 80, 80, and 70. Yeah. So in this, first let me uh, the again the compatibility will be right. The compatibility is initially you apply force D. So let me write. So what are I'm just clearing it now. So this is gone. So this is gone. So yeah, this is my right now. This is a determinate structure, right? So if it is determinate structure, what is my for the loads? What is my say my load? What is it? Dy. Yes. So I have a redundant force one here, and my redundant force D in vertical direction. This is my force. I'll just mention it as F. Okay. This is my F. So now, because of because of the truss, because of the determinate truss, this is my determinate truss. So let me draw it again. This is my truss. Okay. Because of determinate truss, my loads acting 70 here, 80, 80, and there's no force here, right? Now, because of this, I will have delta acting here. All right. I also have what is this? This is dv. Yeah, there is a vertical delta 2 acting here. So how do I find delta 1 and delta 2? So delta 1 can be found out by actually replacing it with unit load. What I'll do is replace it with unit load 1 kilonewton, and then because of this 1 kilonewton, let me say I have internal forces generated because of that, and I'll write it as ui's. Okay. Now how do I find delta 2? So my delta 2 will be, I'll apply a unit load downwards direction 1 kilonewton, and because of that I will have internal forces vi. Okay. So my delta 1 is going to be summation fi ui li by ae. My delta 2 is going to be summation fi vi li ae. Okay. This is my delta 1 and delta 2, but that is not what I actually want, right? Because I also want my redundant forces f and v f and dv. So for f and dv, what I'll do, I'll also find out ui square li by ae sigma, and I'll also find out vi square li by ae. So let me just say it as delta 1 dash delta 2 dash. Okay. So Now
delta 1
delta 1
plus
plus
f
F
times sigma
times sigma
ui square
ui
li
square li
by
by
ae
ae
plus you should also
plus you
mind
should
here
also
because
mind here because
right now I'm
right now
applying
I'm applying
force F, right?
force
So
F,
you will
right?
also
So you will
have
also have
the
the
displacement in
displacement in
vertical
the
displacement
vertical
at D
displacement
also.
at D also, right?
Uh,
Uh,
sorry.
excuse me. Yeah.
So
So
when you apply
when you
force
apply
F
force
here,
F here,
it will
it
also
will
have
also have
the
some
displacement
displacement
at D,
at D,
right?
right?
So that has
So
to
that
be
has to be
accounted here.
accounted here. So
In that
in
case, what
that case, what
happens? It
happens?
is
It is
you also
you
get
also get
F
F
times
times
you
you
also
you
get
also let me just erase it and then you can directly write down. Okay.
so
So
because of
because of
again
again
this
this is
yeah
yeah.
so
So
let me
let
just
me
write
just
here
write
because
because
of
of
force
force
F
F
we
we
also
also
have
have
vertical
vertical
displacement
displacement
at D
at D.
that has to be
That has
accounted.
to be accounted, right?
So
So
that
that how do you write that? So
that is
that is
again
again
that will
that
be
will be
so what I'm
so
saying
what
is
I'm
this
saying.
is
So
my
this is my
delta 1,
delta
this
ones.
is my
This is
delta
my
2,
delta
and
twos, right? So
delta 1
delta one
that
that should
should
be
be
delta
delta
two
2
double dash.
that will be
That will be
sigma
sigma
F
F.
okay
Okay,
sigma F
sigma F.
and what is that
And what is that? Sigma
sigma F
sigma F
UBG
UBG. Or
UBG
U, what is this? UBG is nothing but yeah, this one.
sigma
So
F
sigma F
VI
VILI
LI
by
by E
AE.
okay
Okay,
that is
that is because of
delta 2 double
delta two
dash
double dash.
and what about
And what
delta
about
1
delta one double dash?
that is going to
That
be
is going to be
sigma
sigma
DV
DV
by
UILI by
AE.
AE.
Uh,
Uh,
do you have any
do you have
questions
any
in this?
question in this?
No.
Yeah. So
Yeah.
what I'm
So
trying to
what
say
I'm
is
trying to
because
say
of
is because
F
of F,
you will also
you
have
will
a
also
vertical
have a vertical
displacement here,
displacement here,
and because
and
of
because
D
of
you will
dv,
also
you
have
will
a
also have a
shortening over here.
shortening
So
over
that is
here.
what
So
I'm
that is what I'm
incorporating here.
incorporating here.
So with this
So with
you
this,
need to
you
just
need to just
delta 1 plus
delta
delta
one plus
1 dash
delta
plus
one dash plus
delta
delta
1 double
one
dash will
double
be
dash will be
0,
zero.
delta 2
Delta
plus
two plus delta two dash
delta
plus
2
delta
double
two
dash will
double
be
dash will
0.
be zero.
So we have
So we have
F
F
coming here,
coming here,
DV coming
dv
here,
coming here,
and
and
in this we'll
in this
also
we'll
have
also have
UI,
UI, right? So UI is
what is
what
UI?
is UI?
UI is
UI
F,
is F,
sorry, F,
sorry F,
and VI
and VI is
to be
to be
multiplied with
multiplied with
DV.
dV.
Let me write this again.
Let me write complete statement.
So
So
yeah,
with that it will be easy.
so
So
delta
delta
1 plus
one plus
delta 1
delta
double
one
dash,
dash plus
delta 2
delta
double
two
dash
double
is
dash is
0,
zero.
delta 1
Delta
delta 1
delta one double dash.
delta 2 plus
Delta two
delta
plus
2
delta
dash plus
two dash
delta
plus
2 double
delta
dash
two
equal
double
to
dash
0.
equal to zero.
So delta
So
1 is
delta one is nothing but
sigma
sigma
Fi
Fi
Ui
Ui
Li
Li
by
by
AE
AE
plus
plus
what is delta 1
what is
dash?
delta one dash?
Delta 1
So
dash is
delta one
nothing
dash is
but
nothing but
uh,
uh,
displacement over here
displacement over
because
here
of
because of
the redundant
the
force
redundant
F.
force
Okay,
F. Okay,
so that is
so
going
that
to
is
be
going to be
F
F
times
times
delta
delta
Fi
Fi.
sorry
Sorry, no, sorry.
sorry
It's not Fi.
this is
This
U
is U I
I
square
by
Li by
AE
AE.
plus now what is
Plus now
delta
what is
1 double
delta
dash?
one double
Delta 1
dash?
double
Delta
dash
one
is
double dash is
display
display
displacement
displacement here or the
relative
relative
displacement of
displacement of
CH
CH
due to
due to
the
the
load applied
load
at
applied at
D. So
D.
that is
So
nothing
that
but
is nothing but
dV.
dV, right?
So
So
dV
dV
sigma
sigma
is it
is it sorry, it is dV, not let me just recorrect it.
is
It is
directly
directly
dV
dV
times
times,
okay
okay,
this is going
this
to
is
be
going to be dV sigma
ui
ui
square
square
li by
li by
ae,
ae.
that is going
That
to
is
be,
going to be,
sorry, vi
sorry,
square
vi square
li by
li
ae.
by a, that is 0.
Now what is
Now
delta
what is
2?
delta 2?
Delta 2 is
Delta
nothing
2
but
is nothing but
sigma
sigma
fi
fi
vi
vi
li by
li by
ae
ae
plus
plus
dv
dv
sigma
sigma
vi
vi
square li.
square li.
Is
Is
it
it
vi
vi
square
square or
li
ui
li
square
by
li by
ae plus
ae plus
f
f
sigma
sigma
u
u
ui square
ui
li
square
by
li by
ae,
ae,
that is equal to
that is
0.
equal to 0.
So we have two
So we have two
equations,
equations,
two unknowns.
two
What are
unknowns.
those?
What are
F
those?
and v,
F and v,
and we can find
and
out.
we can find out.
So
So you want the
solution
solution
also,
also,
or
or
No, you can give the answer. I will just
yeah, yeah,
yeah,
copy
yeah,
and paste it
I'll
later.
just yeah, I can give the answer.
dy is
Dy is 96.5
96.5,
96.5 kilonewtons.
is acting
This is acting
upwards,
upwards,
and f
and F
is
is
34.1
34.1
kilonewtons
kilonewtons
tensile.
tensile.
Yeah.
Yeah.
So
So
even if you
even
have
if you have n number of
n number
n
of
number of degrees of redundancy, then
you
you
can
need to again
formulate
formulate
different types of
different types of you need to formulate compatibility conditions, and then you need to use this thing. You need to use
you need to use
you need to use that uh,
compatibility
compatibility
conditions to
conditions
find
to
out
find
the
out the
redundant
redundant
process.
process.
So
Yeah.
any
Any
questions or any
questions or any
clarifications?
clarifications?
This is question of the code. I have never encountered any indeterminate